Hello everyone and welcome back to our Geospatial Python series. Today we will learn the basics of raster data with Python, or how to work with raster data. And we will be looking at the Rasterio package. It is used for raster analysis in Python. It's quite popular. So that is what we'll be looking at today. As you can see, I linked the website. So when you come here to the documentation, there's a lot of things you can learn from here. But don't worry, I will introduce you to it as well. But if you need extra information, you can check out the documentation as well. So before I begin, let me, as always, introduce you to the data I already have. You can see I have 3 files in here, each of them with their names in what they will be doing. And there is the data folder, which usually contains the data we'll be using. 01 data contains a DEM, and then the 02 data contains some bands, satellite images from Sentinel-2. So that is what we'll be using. If we come to QGIS now and inspect our data here, the DEM, you see that this is the DEM we'll be working with. But of course, we'll not be working with it here in QGIS. We may be making reference to it once in a while. But today we are working with Python. So let me even remove this one. I just wanted to show you that that's the data we are working with. And come back to Python, VS Code. So we'll begin as always with a few imports. I'm using Python 3.8.18, as you can see at the top there. All the packages are in this requirements.txt. If you are new, make sure you check the link in the repository. It will guide you on how to install it and get exactly the same environment I am using. We will start, of course, by making some imports. I usually like to import OS because I'll use it for a lot of stuff like navigation, folder navigation and stuff. And we will also import NumPy as NP. We will need Rasterio itself, of course, because that's what we are using. So import Rasterio. Usually it's imported as real. And we will also need some other things, but we'll come and import them as we go along. Let me try and make this one a little bit large. So once the run is successful, that means that I have Rasterio installed and the other packages are imported as well. So the first thing is, how do we open a raster data? Like when I went into QGIS, I just dragged and dropped it and it worked. So how do we open it like this in Python? I will start by declaring the file path. So let me say DEM path. Then I'll say os.path.numPath, normalized path. I think this is PATH. My IntelliSense is not popping up today. And what I'll do is to come here, navigate to the data itself, right click, and then copy path. I like to copy the full path and not the relative path. So let me just paste that one in here. So that one is our DEM. And then now we can read this file. Like we say in programming terms, to open the file means to read it. It's quite similar to how we open files by default in Python, just that this one, instead of just with open, we now say with rasterio.open. But because we imported this as real, we say real.open. And in here, we pass a few things. Of course, you have to pass the file path. So that would be the DEM path. Something is happening somewhere because I'm expecting my IntelliSense to pop up. But it's good that it's not popping up. Sometimes it does block my code and Usually you have to also pass in the mode we are reading the file in, and by default it is read. Let me see if the documentation will pop up. Okay, it is also not popping up, but the mode is read by default. So if you don't pass it here, it will still work. And so we can continue to read it as, by convention, you will see people reading it as SRC. Now this here, if we print what SRC is, you will see that it's a Rasterio dataset reader. So this SRC in itself is not the bands we are looking for. It's a dataset reader that contains all the bands in here. So if we actually come to the documentation, I think that should be the Python quick start, maybe. Opening data sets. Okay, it says here that it returns an open dataset object, and they have some attributes as well that you can explore them, but that will not be really the focus of this tutorial. So now that this SRC is not really the band we are looking for, how do we get access to the band? Well, it turns out that is also quite easy. If I want to get the band, I will just read it from this dataset reader. So think of it like, before you access the bands, you first open the files into a dataset reader, and then you read the bands now from the dataset reader. So if I want to read a band, of course, this is just one band. If I want to know the number of bands in my raster, I can do print src.count. And you see that is 1 because I have a single band raster. There are other stuff like src.meta, which contains the metadata of the raster. You can see here. If we want to see this one properly, I think we have to now extract it into a variable, then we can loop over it. So meta equal to src.meta. And then here we can see maybe for key, comma value, because we can see here there is a dictionary. So key, comma value in meta, we want to now print the key and then the value, but let me put it in an F string. So the key, and then we will also come here with the okay, it's V and then K. So if I now run this, okay, I think this is like this. Okay. Okay, the meta.items, it is a dictionary, so meta.items. Then we get it here. So the driver is a geotiff, and the data type is an integer 16, and no data value is this. And there's this transform here, which is the affine transformation, which we use to do the transformation from pixel to spatial coordinates. And so when we get there, we'll get to know what all of these things mean. You can also get the src.height. That one too is there. So there are lots of properties you can get from the actual raster file itself. So if I say print src.height, it will give it to me. src.width, that one too will give it to me. But if you want to access the band, in this case, we know that it's a single band raster. What we do is say src.read. And then in here, if we only have a single band raster, like in our case, then we don't need to pass the index here. Now, what is the index? The index, if we print src.index, you see that you have 1 here. If it was a 3-band raster, it had, let's say if it had any number of layers like 7, 5, 6, all of them will be listed here starting from 1. So this is not like your regular Python indexing where you start indexing from 0. This actually starts from 1. So we can now, if it is a single band raster, we can leave this place blank, but if you specifically want to read band 1, you can put 1 here. If you want to read band 5, band 6, you can put the 6 here. But I'll leave it as 1 here. And then now I will print band. Or let me say the type of band. We know that the SRC is a Rasterio dataset reader, but what is the type of band? Band is a NumPy ND array. That is why I imported NumPy at the top here. So I want you to get this understanding from this place, and it will really be good foundation for us to build upon for all the things that relate to raster, I'm sure. Because a band, as we know it, or as it is just an array of numbers. So think of it like a big matrix. Rows and columns, each of them have their digital number, but they are just numbers. If we come to QGIS and let's load our DEM again. If I zoom into this side, now I can see the pixels. Maybe they are not showing well on your screen, but if you follow along, you also have access to that. You see that this is the pixel, the one that has been highlighted red. Now, this pixel, of course, is band 1, so only one band. The height value, because this is a digital, the elevation, because this is a digital elevation model, is 73. So we can say that is the digital value or the digital number. But because this is an elevation raster, that is the elevation of that particular place. And you can see here that we have click coordinates, but because I clicked on column 0, row 0, that's why we see that the column base is 0, the row base is 0. 0 base is only trying to tell us that it's starting the counting from 0. So, but if I click here somewhere in the somewhere inside, you see that now I'm column 5, row 4. Because I count 0, 1, 2, 3, 4, 5, and 0, 1, 2, 3, 4 here. So think of all of these things that you see here. It's just a big grid of numbers. That is why we are able to read it into a NumPy ND array. And the advantage of it is that if we have used NumPy before, we can perform all sorts of heavy mathematical computations with it. We can, together with other packages for working with data or multidimensional data like XArray, like SciPy, and all of those powerful data science libraries, we can just use this NumPy array and then perform every other computation we want to. So that is it for the band. Let me, I like to close the file so that I don't have any memory problems. We can bring it back anytime we want to. So we know that it's a NumPy ND array, but what if we print band itself instead of the type of band? Now, this is what we are seeing. As I told you, just think of it like a big matrix. If we are new to NumPy, we will not really be doing NumPy, but if you're okay with NumPy, it's an ND array. If not, just think of it like a big matrix of numbers. And this here we see 73, 73. These are what we call the digital numbers, or the digital value, or the value of the pixel. And here, because it's an elevation raster, when we clicked at first, you remember we saw 73, and I told you that's the elevation of the place. And that is, of course, the first pixel, the row 0, column 0. So we can perform all other NumPy operations we want on this one, but because this is just a raster basics and introduction to it, we'll not delve so much deeper into those things. In subsequent tutorials, we'll look at how to use this bands for any other remote sensing applications that we have been doing with software, and we will get to know that it's very easy to work with these things. Now, we have seen this, but of course we can also try and plot it or make it visible like we saw in QGIS. So how do we show, or how do you visualize the raster, not as a programmer or data sciences would like to see it, I mean, in terms of ND array and numbers, but maybe we want to just see how the DEM looks like. That's one. We need some few imports here, so I'll add them. Rasterio comes with a plotting manager as well, so I can say from rasterio.plot. Here I want to import show, and then there's also another one called show underscore hist, is for showing histogram. So you see all of them. So let me give a markdown here. So this one will be opening a raster file, and then another one here showing a raster file. Did you run this place again? I don't think so. And if you want to show it, then what we can do is, now we can show the band, we can also show the dataset reader itself. So I'll tell you the difference between the two. The first one, let me show, and then let me show the band. If I run this, you see that it gives me the DEM like we saw it. I can give a title of, say, digital elevation model, and this, I think the color map is already fine, but you can also give it a different color map if you want to. That is C map. And here I can say I want the terrain one. How do I know that it's called terrain? I'll show you very soon. Usually for values like this, there are fixed values in the package that is used for visualization. So if you type in anything wrong, like ABCD, and you run, it will tell you that ABCD is not a valid value for CMAP. Supported values are, and it will list all of them there for you, so you can go through and pick the one you want to use for visualization. So I'll go back to terrain, and this is it. The only what I would say problem is that if you look at the axis, the coordinates are starting from 0, 0 here, and it doesn't look like they are real world coordinates. And now, as a matter of fact, they are not real world coordinates. If we come to QGIS, we may not really see that, okay, but we can target the extreme and the right bottom pixel and then see what the coordinate is there. So if I bring back my DEM, and this time around try as much as I can to, okay, this one is the last pixel here, and we know that the coordinates, x coordinates here and the y coordinates here, this is 0.01, this is 5.56, but if you look at this plot we have here, this is going way beyond 700. So that means that if we plot the band like this, we may not really be able to show the correct geographic coordinates or the correct geographic values on the axis. If we want the values on the axis to be matching to the appropriate geographic coordinate, we don't have to show the band, we have to show the SRC. But usually in this case, it will tell us that the data set is closed, because after the width block, then this data set is closed. So everything outside this width block, we cannot really access the SRC like that because of how the width works. So I'll copy, and then if I really want to also do it, maybe I can bring this line here, and then let me bring it at the top. Then here I can show the band. I mean, the band is already at the top there, so it's not necessary for me to show it, call it again. So I can also put this one here, and this time around put SRC here. So this is digital elevation model, or let me make it DEM, and this is the SRC, and then this is DEM band. If I run now, see I have one DEM SRC. This one now corresponds to the correct. You see that the coordinates here are correct. When we explored the data set, you saw that the coordinate reference system is in EPSG 4326 WGS84 Geographic. And this one is the band, the NumPy ND array that has been plotted. So in case you are plotting, just know the difference between the two. If you want to, maybe you have done any analysis, you want to export as a map, and then you want to plot the SRC itself and not the band. All right, so we have now seen how to, let me give comments because I will upload this. Or maybe after the video, then I properly comment it out so that you have access to it. So this place is showing the band, this place is showing the data set itself. Now, how do we now transform from pixel coordinates to spatial coordinates and the other way around? Because now we see that there are two different plots. They look the same, almost the same, with the exception of the coordinates. So how did it manage to plot it exactly the same at the same geographic space? And that is what the affine transformation will help us to do. So let's see how we will do that quickly. I also said I will show how to plot the histogram. I forgot. So if I comment out the band itself here, and then here I duplicate this line, and then I can say show histogram. This one I don't really think, the histogram doesn't have a CMap, and I think it only has a label and not a title. So if I say DEM histogram and I run it, I now have an error, show hist. I forgot the T. So this is the histogram for the raster also. And so if we want to transform it from, or let's say we want to like get the coordinates in terms of pixels and rows and actual spatial coordinates. Well, we are opening it a lot, but I think it's okay because it closes it as every instance, so we don't really have a problem, and it's also good for the tutorial. Now here, let me say transforming from pixel coordinates to spatial coordinates. I will paste again. This code, will be writing it a lot, so let me just come and copy. We are not showing these things here now. And what we need here is the affine transformation. So the transformation, the transform, that equal to src.transform. We can of course print it out and see what the value is. So if I print transform, that is the transformation matrix. If we pick any pixel coordinate, so let's just say that if that was the case, then we don't even need to repeat this code here. We can get it from here where the band is. So when we say transform, and remember the coding principle, do not repeat yourself. So src.transform. Then we have it to use it everywhere else in the code. Now, I can say that the pixel coordinate, that's equal to, let's pick it from QGIS. So this particular pixel, the row is, well, let's pick one which is inside somewhere in the middle. So that's our pixel here, 307 by 231. 307. Oh. 307 by 231. And this one we want to now transform it to spatial. So its equivalent spatial coordinates that equal to the transformation matrix, so the transform, multiplied by the pixel coordinate. If we print it out, let's say print, and this one should be pixel to spatial. What we will get is our spatial coordinates. If I print it, I get this value, which is negative 0.09 and then 5.6. Let's see if this is correct. So that is negative 0.09 and 5.6. Of course, decimal places notwithstanding. But that is the value. You see that now you have been able to transform from the pixel coordinates to the spatial coordinates. Now, what if you want to get the reverse from the spatial coordinates now back to pixel coordinates? That one, we can say that the reverse coordinates, and then let me copy this value and paste it. So if everything works well, then it should return the 307 and 231 for us. And then pixel index, that is what I would choose to call it. So pixel index, and that should be equal to, now we will not use the transformation, we will use the index of the source file. We printed this, so if I print src, I don't think we printed that one. So src.index, you see that it's a transformer method mixing. We may not really need to go into all of that, but it uses this one to also transform from the spatial coordinates to pixel coordinates. So do we need to, maybe we need to call that one too. And so say index, that should be equal to src.index. All right, so we can come down here and say index, which we have at the top there. I don't think we can call this one like this because of how we are supposed to do it. So, or let me just try it and see. So index, and then we can now, it will not work this way because we are it's something that we are calling. It's not just a variable. So src.index, and we can now pass the reverse coordinates. This is the first value. No, reverse coordinates. These things would have been fixed by my IntelliSense. Maybe I'll have to refresh it and then make sure that it works. And then another reverse coordinate. This one, then we fix the second one. If we print, okay, let me just copy this one. Or even cut it, come and paste it here. If we print pixel index, it says reverse coordinate is not defined. Okay, S. Then now we get this value here, which is 230,307. Of course, we can give some reason or blame to our number of decimal places. Let me try and reduce it and see. Okay, so it has to do with decimal places, but you can see that originally it was very, very close. I mean, And maybe we have to find some perfect ground somewhere in the middle so that we can get it back accurately. But this is how you transform also to from spatial coordinates to the pixel coordinates. All right, so let's go to the second notebook where we will learn how to create composites. But before then, I would like to refresh my VS Code. I think there's a shortcut. Let me see. So reload. So hopefully our IntelliSense is back. Let me see. Okay, now it's back. So import. And here we will import OS as always. We will also, let me make it a bit larger. Import Rasterio as real. Maybe you will need NumPy, so let's import NumPy. Also as NP. And this time around, we will be using the bands in here in the 02. So I'll copy this path for the bands themselves. And then here, I'll say rasters path or dir. That should be equal to os.path. NumPath, and then I'll pass in this path. All right, so I can now get all the files in here. What I also want to do is the file types are all they are not TIFs, now they are JP2 files. But there is a way I love to read this one so that when I'm creating any kind of composite, it will be easy for me to identify the particular band that it is. Of course, we can now use glob or even os.list directory to list every file in this particular directory, which is a JP2 image. But I like to do it in another way, and I think you like my style. First of all, let me just say raster files. That should be equal to, let me import it here. So import glob, run it again, and there's a raster there. There's also, let me minimize this one, raster files. That will be glob and then .glob. Here I pass in the path and then the specific file type I want to search for. So I can say os.path.join. I want to join the rasters directory with any file in there that is .jp2. So this one will give me all the files in there that ends with .jp2. Usually when you work with some raster files, they create some XMLs and stuff. So you want to make sure that when you are reading from that directory, you don't read everything in there, but you read with the files extension. And so if I print now raster files, of course it will be a very long list. So let me just say for I in raster files, then I want to print I. So now I have these 4 bands here, and you see that it's not really bringing them out in a sorted manner like I have in there. So what I want to do is that this one I can now pass sorted here. I can pass sorted, and then now I get it sorted here for me. All right, so I know that I will not make a mistake if I'm referring to band 2. It will be band 2. I mean, it will be the first, 3 will be second, 4 will be third, and then 8 will be fourth. So here now I can see that files, that's equal to, let me make it a Python dictionary. And I can say that the, let's inspect what is the Sentinel 2-band configuration. So the band 2 is blue, band 3 is green, band 4 is red, band 8 is the near infrared. Let me copy this one here. And then let's come back to VS Code. Let me paste it here for it to guide me. So if I want the red band, then I will, because now this is sorted here, I can use Python indexes to get it. So I can say raster files, and then the red is the band 4, so that will be at the second index. And then I can now duplicate this line. Now if I come to blue, the blue is band 2, so that is at my index 0. And if I come to band, the green band, that is band 3, so that is my second item. And then the last one is the NIR, near infrared. That is band 8, that will be my fourth item. So this is done. Maybe to make it nice, I can rather bring the blue on top, and then I'll follow it to the green, just so that it moves from 0 to 3. So now if I want to do anything with this, if I print files as I have it, so files, and I access the blue and I print that one alone, it gives me the full path to that file, and that is what I'm looking for. So what we can do now is to create a little function to help us read bands. So we call it function read band, and in here we'll say take the file path, and we can say with real.open, and we pass in this particular file path as maybe data set. You can open it as anything, you are not restricted. So I can say return datasets.read, and then I want to read the first band. Of course, it's a single band, but I still want to pass one here. And here I can now also read these bands into a dictionary again. At first, it may really sound a bit maybe confusing, or maybe that I'm doing so much work in reading the bands, passing them into dictionaries, while I can easily read all of the files in there and then work with it. But we really appreciate it if you do large-scale works with Python. You like my style. Now, what I want to do is the bands, actual bands, now is I'll first write it the regular, or let me say the old-fashioned way, and I'll write it as a dictionary comprehension. So I can say for band, or let me just now create a new dictionary that will store our bands. And here I can say that for band, or no, for file, in files, what I want to say that bands, that particular file, sorry, I have to even pass actually the file itself. And then here I will say that's equal to read band, read band, and this will be files, file. I mean, it's becoming a bit, maybe is it too much, but this, or let me just print out bands, and then we'll see what is in there. So bands now is just a dictionary of several NP array, NumPy ND arrays. So you can see that we can actually now call for band, and then in here we pass say blue. I shouldn't have been reading this one multiple times. Let me cut this one off, and then a new cell should be doing this job, because band is already read into memory. No need to be reading it multiple times. And yeah, so a new code cell, that is where we'll be doing the other stuff, so that we don't keep on reading what has already been read before into memory. So we know that now this will give me all the bands as NumPy arrays. And remember, I told you in the beginning that this is just a NumPy array. So if you want to stack it, it is quite easy. We can say now that our RGB composite, which we know is 432, or the red, green, blue. Sorry, it's not really 432. It's red, green, blue. That will be np.dstack. And you see that this stack here stacks arrays in sequence of depth wise along the third axis. So it will just stack them literally on top of each other. That's what we want. So this stack, and then we pass in our bands. So that will be bands red, and then bands green, and then now we can see bands blue. So this is where my style of reading it really comes into play. Like, you really get to know that, okay, I'm reading this band, instead of you keeping the indexes in your mind and be wondering whether 0 is 1, 0 is red, or whether index 2 is blue or green or whatever. You can just call it this way, and I think it's more cool. So now we are stacking, but there was one more thing I was supposed to have done, is that I have to pass in this value also itself as a tuple, so to be 2 round brackets before I pass in my bands. Now this is already done. We have stacked the bands. If we, of course, we can think, have you already imported show at the top there? I don't think so. So from Rasterio .plot, we want to import show and run this particular cell again. If we run this cell and then now show our RGB, it now says invalid shape for image data. All right, so one of the things I think can fix this is to normalize our image. So let's now define a normalization function here. So define normalize, and then this one takes in an array, which is our NumPy array, and then we can just say return. Let me just give a simple normalization function, return array minus array dot minimum. We can enforce this to say that this array should be an np.nd array. All right, so that you can leave it like that, but I mean, I like it this way also. Divided by the array dot max minus array dot minimum. Okay, so if we now say that RGB normalized, that should be equal to normalize, and then we pass in the RGB. Now if we try to show our RGB normalized, We have to run this one, of course. We still have this particular error showing let me add a particular constant here to see. So 1 exponent -3. Actually bring this one to here. So now let's inspect the shape of these bands. Let me see for band, comma, the shape of the band in bands.items. Here we can print the band. I like to use F strings, so the band, and then the shape. Okay, there's a band dot shape. Or its size. Okay, it's saying a string item. So okay, that is it has to be this way rather, maybe for I, which is for the index of the item, and then band here. So we can say I, and then the band now is the numpy array that we can now call the dot shape on it. It's not callable. So we have the blue band being this, and I don't know why it is saying that the shape is wrong, because all of these things have the same shape. So I don't understand this particular error down here of the shape. Okay, so I found the error. It appears that this D stack returns, it says the equivalent concatenation along the third axis. This is MN1, and then, let me just explain it less technically. If I print the shape of RGB here, RGB dot shape, no, this is not callable. Why do I call it always? I get this. And let me try and print the shape of RGB normalized also. This one too, so print RGB normalized dot shape. Okay, this is what we get. But if we look at our error, it says it has 8742 and then 3. It has swapped the band axis into the middle, and that is why it is not able to plot it. Even though here this is how it looks like, of course that is how it should look like, but in here you see that the matplotlib IM show is saying that this is now the shape for our data. If we want to get around it, then we can forget about this D stack and use the actual stack rather. That one will bring us the shape like we want it. So instead of D stack, we use stack, and then that should give us what we are looking for. Okay, so now we have this image here showing, and of course this is our bands. Why the surface looks a bit darker, it has to do with our normalization. If you have worked in Google Earth Engine before, you know that sometimes getting these satellite images to be very clear, you have to really experiment with a lot of values. And so this normalization function only is a simple normalization that gives us, it takes the minimum and the maximum array. But the problem that comes with this minimum and maximum array, and maybe throwing some value also here, is that if there are some errors at the edges of the image, let's say at the very edge of the tile, for an elevation raster, and let's say that the highest elevation you know should be like 100. If there's an error at the edge of the image, it can now make it like 500 or 200. So if we just take directly the minimum and the maximum of the entire array, I'm sure we may be having some problems where there are some outliers that we will still factor in our computations. And so what I like to do is to rather take some percentiles rather than taking the entire values. So what I'll do is now to take between 2 and 98. So all the values that fall between 2 and 98 percentile should give me that one instead of the entire array. So I can get what I will call the array minimum and array maximum. That I can set equal to numpy.nan percentile, and then I pass in the array, and here I want it to give me from 2 to the 98 percentile. So you can see here that this one compute the kth percentile of the data along the specified axis while ignoring the NAN value. So yeah, so all the NAN values are 0, and when we printed the value of the SRC, I think this one we have not really printed it, but if we come somewhere here, are we reading it somewhere here? And if we are supposed to print SRC dot meta, we will see the no data value there. So we don't want all of them in case there are NANs to be included. Also, and then here now we can, now instead of returning, we can, let me get rid of this for now, np.clip, and then we clip array itself minus array minimum, and then here I can say array max, array max minus array minimum. Okay. And then here, this clip function, you know, it requires all of these ones, and then some other values that we have to also pass here also. So we want to say that should stretch our normalization between 0 and 1. And then we can now see if this will really, let me get this one off here, run this normalization. Then afterwards we will show it. So now I can come here and say show RGB normalized. Hopefully that will improve it a bit. If not, then we have to keep on experimenting with the values as well. Okay, so now we see here that the normalization function really worked. Now our image here is very, very clear. Also, the previous error the reason why they says that the array was maybe, let's say, flipped, that was not really giving us the values, or it was not plotting and giving us an error. I forgot that instead of using rasterio plot.show, I was supposed to use matplotlib.imshow. So if you still use the D stack here, it will work. But in that case, if you want to visualize it, I forgot that one, forgive me. You have to or import matplotlib.pyplot as plt, and then instead of using this rasterio show, you can now use this plt.imshow to show the dstack raster, the one that you use dstack for. But I think that part is now past now, so I'll rather continue with what we are doing now. But I forgot. That is why I was so surprised with the error. I just looked through my notes and I saw it down there. Sorry about that. But this is RGB normalized. I really like this image already. Very, very fine. So you see that there is an advantage in using the percentile over the general minimum maximum. We can even make it finer by tweaking the percentile value, but we'll not do that here, of course. So now we have got our RGB normalized. How do we save this particular raster so that maybe you can open it up in QGIS or somewhere else? Of course, you can see that this is, of course, is the band. We see that the values here are not really true, the coordinates. So here is about saving the composite raster. Before we save the raster, we need we have the band now. What we lack here is the metadata that we will add to the file to make it one that can be represented in the geographic space. So what we can do is to now get those ones from the original file. Any of the bands themselves can give it to us. Then we now use those ones to save the file. So remember that we still have access to our bands here, so we can read any of them. And that will be bands. Let's just read the blue band. So with rio.open bands, and then we get the blue as SRC. What we want to get is that the meta equal to src.meta. We are not really changing a lot of things in here, so we can use that metadata to do to save the file. But if we let's just print this meta and see what it is in there that we have to change. It says what? Okay, this has already been read into a numpy. These are the arrays themselves. So what we need is I'll call files rather instead of bands. So that will be files. Sorry. So this, we have our node data, and this count value here is 1 because this raster we just read is a single band raster. So we have to update this. Other than, and that is it. I think the rest stays the same. The width and height do not really change. These values, if I copy them and come up here, let me paste it here for comparison. Yes, it doesn't change. So those ones, we don't need to change it. We only have to change it if we're doing some cropping. So let's now update this metadata and change the count value to 3 because it's a raster 3 composites or a composite of 3 bands. So we can now say meta dot update, and here we say that we want to update the count to 3. So we can confirm it by still printing out our meta if the update really worked. And now our count is 3. Fantastic. So let's now use it to save our raster file. Here now we can see the with real.open. Again, I'm still indented inside the first with statement, and here we have to pass in the file path. So what I will do here is I will say composite path. That should be equal to, we already have an output directory here, so I'll copy it. And this will be os.path.join. Let me give another output part here because it will be a very long one. I don't want to, I want everything to as much as possible be on the same page. So os.path.numpath. And here I pass in the path to this particular folder. And then here I can join the output path with the file name, which is maybe composite.tif, TIFF. Because this geotiff here, I think it should be showing somewhere. Okay, it's now J2. Okay, so we can leave it like that. So we just say JP2 so that we keep it like the original files themselves. You can see here that they have JP2 extension. So let's keep it like that. So now with real.open, here we pass in the composite path, and then we now specify that the mode is now write, and then here we have to pass in the metadata we want to save the file with. So we can use the spread operator here to now spread the metadata. And then here we also have to open it as maybe DST. By convention, that's what is usually done. And then I can say dst.write, and then I will write the RGB normalized. Okay, before I run that cell, if I take it to the output folder, you see here that it's completely empty. I refresh and it's still completely empty. But if it's successful, then this one should give us a file in there. You can see that it came in right away, composite.j2p, jp2. Sorry, so let's come to QGIS here. Let me now remove this DEM. And let me try and bring in that particular raster composite. Okay, we don't really have so much of a nice raster here, but if we inspect the properties of this raster, it has 3 bands in there, and for the colors we can use symbology to work around it, but you can see that these are the properties here of the raster. All right. So that is also how we do the composite, or maybe we should now rather, let me see if I save the RGB itself, so the RGB normalized, whether the colors in there will change a bit. Okay, so then I recommend that the normalization is only for visualization. I forgot to say that, forgive me. But if you are saving it, make sure you save the raw RGB, because these softwares, when you load it, I'm sure they also have their on-the-fly normalization they do to just make sure that your image appears nice. So if you already bring it in and already normalize the image, maybe that is where the coloring becomes very bad. But I'm already liking this particular raster already. If I bring in the data, any of the others, see that this is the original band 2 image. If I come here and turn it off, this is the composite that we created. So that is it. Very nice. Of course, I don't really want to leave this page now. Let me leave it now and come back to code, and then let's continue. So that is it, also saving composite. If you have a lot of work to do, you can now plug this into a function, and then you can easily run it for multiple files. The third one and the last one we are doing for today is to learn how to do reprojection and clipping. So if we maybe now work with our composites, so let me remove it from here. I will of course bring it back. It's so nice. Let's start first with the reprojection, and then now we can do the clipping. For that one, we still need our import. So I'll import this screen. The IntelliSense is also not trying to work again here. Import. So let me refresh or reload the window again. Here we have import, and then you can say Rasterio, still not working. As real, but no problem, we can proceed without it. And here I also want to import PyProj. Okay, now it's back. We use it for the projection because we are doing reprojection, of course. And then I usually like to import the defaults, let me say the traditional Python packages at the top. So OS here. Here you will not need NumPy, but from rasterio.warp, we want to import, calculate the default transform. We also want to import reproject from the same place, and then resampling also. I think that is all we should need for now. We will come back and add those ones for the clipping, or maybe we should just add it and then we will not come back here again. So for that we also need GeoPanda. So let me import this one from Rasterio first. Rasterio.mask, that is what we'll be using to do the clipping. So import mask, or import Rasterio from Rasterio.mask, import mask. But why is it not showing? Okay, from Rasterio.mask, import mask. And we need GeoPandas too, so we import GeoPandas as GPD. Then we run this. All good. So when we want to reproject, of course, you have to declare the reproject, the path of the raster we want to reproject. And so for now, I'll use the composites. So let me copy path. And then here I can say that raster path, or let's just simply say path equal to os.path.normalize path, and then I'll pass in my file here. All right, so I can now say, you know, this convention already, we have used it many times with real.open, and I'll open path as src, and then here I can print src.crs. Okay, open, and it's in EPSG 32630, the WGS 1984 UTM zone 30 knots, and we want to maybe project it to WGS Geographic, which is 4326. So how do we do that? We need a few things: the transformation, the width, the height. I mean, the new image that is coming in will have a lot of things being different. This one is not like when we are doing composites where we only have to change the counts, the raster counts. And so we have to get first the transformation. We will need the width. We also need the height. And for this one, the calculate default transform will give it to us. So if I spread it on different lines, we first need to pass in our source. So if we put our cursor on it, you see that we need our source CRS, our destination CRS, our width, height, and the rest, left, bottom, top, and stuff. So our source CRS, that will be src CRS. That will be src.crs, and then our destination CRS, that would also be D. That should be now what we are supposed to put in here. So I can now say dst underscore CRS, that should be equal to piproj. Remember, we imported this at the top there, dot CRS, and then in here we pass in the code of EPSG 4326, not 2526. So this one we can pass it as DST underscore CRS. And then what we need to pass in again, we have to pass in SRC, the width, equal to SRC.width. And then the height, that is equal to SRC.height. Okay. And then the top, bottom, left, and right, we can simply pass in src.bounds. But because we are spreading it, we have to now use the spread operator like this. The star, we pass the star there to automatically spread it for the bounds that we need here. Okay, for the GCPs and stuff, we will not pass it in, but if you want to modify those ones too, you can do that. So as always, we need our metadata. So that's meta equal to src.meta.copy. And then we update to meta.update. Remember, the new file that will be created, it will not have the same metadata as the file that is coming in. Here we want to update the CRS. The first thing, of course, the most important thing to update, that one will be not the source CRS but the destination CRS. We also want to update the transformation, which is the transform to the new transform that will be calculated. We also want to update the width with the new width that we have. And then lastly, the height, not help, the height with the new height that we have here. All right. So this is now our new metadata that we can use. And we need a path for the projected raster as well. So let me put that one at the top here. So projected underscore path. That's equal to, we already have some code snippets here that I can copy. Oh. Here, so this one, instead of composite path, this will be reprojected. And here we can now come and say with real dot open. Here we pass in our reprojected path, so projected path, and then it's in write mode, and you know that we have to spread our metadata. But we are having multiple bands in this particular file. So how to do it safely is we can now say for I in range. If you have a single band raster, you just have to say dst dot reproject, and then you just pass it in. But because ours is more than one, I think the safest way to do it is this src.count plus 1. You know how the indexes work. It starts from, we are forcing it to start from 1, but it always ends as n minus 1, so we have to add 1 to it to make sure that it matches the total number of bands in the composite. And then we can call the reproject here, this one coming from Rasterio itself. And then there's the source, which is our now we are reading the SRC. We can now call rasterio.band and then pass in here the source file and then pass in the particular index. So sorry, this one should be I, not 1. What it means is that for each of the files in SRC, create a band for us in there, or get that particular band. But which band? The band from this SRC dataset that is coming in the dataset reader, but this particular band. So if it's at the first iteration, you get band 1, the second iteration band 2, up to the last band itself. You also have to pass in destination here, and our destination is rasterio.band, and here too we have to specify it, which is our DST file that is going in at this particular index. So we should take it from this place and then put it at this place. There's the SRC transform. Here we do src dot transform, and then you guess right, there is the src crs, which is src.crs, and then we also have to get for the dst transform. So dst transform, that is our transform that we calculated at the top there. Our destination CRS, that is also our DST CRS that we did at the top there. And then you can pass in the resampling. So resampling here, you can say resampling. Then here you can pick a method. You can pick the average bilinear cubic spline, but let me just pick the nearest. All right, so this is it. We have this is how to do the reprojection. You just declare your destination CRS, you open your file, and then get these parameters: the width, the height, the transformation, which this guy will give to us, and then you can now update your metadata from the original file itself with the updated stuff, and then you open your reproject. But if this was a single band raster, all you need to do is to get rid of this for loop and then paste it in here. In this case, it will be SRC band, you know, it's 1, so you can put 1 here, and this one to band 1. But in our case, it's multiple, so we have to now use the for loop to do that safely. So if we now run this, if I open this place up again, now you see I have only the composite in there. Hopefully, if we did nothing wrong, which appears not to be so, then we should have our projected. So it says that it got two values for what? Multiple values for SRC CRS. So we have destination CRS, we have src crs. So why is it saying that we have this? Or maybe let's just delete these ones from here. So we have our source CRS, we have our destination CRS, the source width, the source height, and the src.bounds. Let's see. Now while this is running, maybe I can go ahead, get a new cell, which is becoming difficult for me to do. So in the new cell, I will just now with real dot open, and then I can open the reprojected path. As RP, maybe for reprojected, I can now print rp.crs. So now that this is done, if I run this, I should get EPSG4326. But if I open the composite path, do we have anything like the composite path? I think we called it path. Then that one is 32630. So it's that we have successfully reprojected the raster from UTM Zone 30 to WGS 1984 Geographic. So that is also how we do the reprojection. If we inspect the file, it should be in there together with the composite. And of course, we can come to QGIS, and then in here, it's at output, there is composites, there is reprojected. And the two are in there, and you know that because of the projection, that's why you're seeing those black stuff there. But we know that this is reprojected. Of course, we can check this off, and this one is still here. All right. So now let's go back and see what we can do with. Now we are left with clipping. That is what we have to do now. That is also quite easy. Let me give a markdown here. Clipping. A raster with a shape file. Or a vector file, because I'm not actually having a shape file, it's a geo package. Now, what we'll be using for the clipping is the DEM, because I think it's a single band and not that heavy, so that it will be faster. So I'll bring in the DEM here. See, and then there's this ROI geo package that we'll be using for the clipping as well. So let me now take them from here, and then let's go inside VS Code. ROI path. That should be called to os.path.norm path. So let me go ahead and copy this. Copy path. You can also choose to use the relative path, and that is fine. I mean, if I'm pushing to GitHub, I'll be using the relative path, of course, but I like to work with 4 paths. Now we can see that the GDF, the geodata frame, that should be equal to gpd.read file, and that should be ROI path. Of course, we can inspect this GDF, but we don't need to. So what we have to do now is say with real.open, we want to open the, but we will need the DEM. So let me now also say DEM path, That should be equal to os.path.numpath. That is here. We want to open DEM path as SRC. Here we will perform a check and make sure that the two are in the same coordinates reference system. So we can say that because it helps, we have to make sure that that is the case. Otherwise, we will have an error. So if gdf.crs is not equal to the src.crs, what we want to do is to say that now the gdf equal to gdf.to_crs, and then we can pass in the src.crs. What we are doing here now is to say that if the two don't have the same coordinate system, then convert the geodata frame to, or reproject it to the raster's coordinate reference system, just so that we know that the two are the same. And we need shapes here. You understand why they are called shapes. It's gdf.geometry dot values. So if I print shapes, see that it is shapeless polygon. Okay, so we understand why it is shapeless polygon very soon. And then here too, we need to now mask the image, so we can say that clipped image underscore clipped image transform. It is so because the mask function gives us those two outputs, so we have to pass in now our src, our shapes here as well. Look at the reason why we are calling it shapes is that it takes in shapes here. And here in the parameters, the shapes, it says like the values might be a JSON-like dict or an object that implements Python's Geo interface protocol, such as a shapely polygon. That is why we converted these ones into a shapely polygon, these shapes. All right. Now, we now have to save the image. But a very important thing I want to draw your attention to is that there's a very important parameter here called crop. If you don't specify this crop, something will happen. Maybe I should use the result to explain it better. So let's proceed. Now with out meta, or let me just say meta, that should be equal to src.meta.copy. And then meta.update. Here we want to update the height, because the height value will change. If you are cropping off, obviously it will change. That one, it will be given by the clipped image. Okay, clipped image dot shape the first the index 1, and then another one for the height, sorry, the width, and then here is 2. And then we also need to change the transformation, which is the transform, to our clipped image transform. All right, so we need another part also for our clipped. So clipped underscore path, that should be equal to, we already have our output path there, so that should be equal to os.path.join. Here we want to join the, all right, right, output path with this DEM is TIF, so you can say clipped.tif. All right. Like always, we have to save it saying with real.open, and then here we pass in the clipped path, or not clipped image, clipped path. And then we specify that we are writing, and then we spread our metadata as DST, and here we can say dst.write, and then here we can see the clipped image. So when we run it, now we come here, set our output, there is clipped.tif as expected, and then now let us visualize it. So with real.open, here we open the clipped path as src. Do you have Rasterio.show at the top? I don't think so. So let me import here from Rasterio.plot import show, and here I can show my src. Show you see here that it is showing a clipped image, all right, but the boundaries, the bounding box of the raster is still the same as the old one. And what do I mean by that? Okay, let me bring this code inside here. I want to be able to plot the main raster as well as this one. So maybe this one, let me bring it at the top. Put all the imports here. Run it again. And then here, before I even do that, let me show src. Then give a title of array original, and then come here, this show. Let me also give a title here of clipped. Now this is original, this is clipped. You can see that the bounding boxes are the same. This one should be deleted. But usually that is not the effect you want when you clip. You want the clip to also come or clip it to the extent of the bounding box. If that is what you want, which in many cases is true, then you say here that crop equal to true. When you do it that way, now you see that it is clipped, but the bounding boxes are not the same. This one it goes to 5.68, this is 5.67. And I mean, it's not the same. From negative 0.14 to negative 0.06, and you see here it's quite different. So that is how you maintain it to the bounding box. There's also another very important one here called invert. Invert, what it does is that it will invert it for you. So if I say invert also equal to true, it will not clip using the interior of the ROI, it will clip the exterior. And of course, crop and invert cannot both be true. So one of them has to be false. If I take the crop out and stick with the invert, so now it has clipped it, but the place that the ROI covers is rather now like it has inverted it. So that place is rather no data, and the exterior is rather the place where the data is. I don't know the scenarios where you may need to do this, but in case you have to do something like this, then this is how you do it in Python. But I'll reverse back to the crop rather being true, so that I have it this way. So that, my friends, is how we work with Rasterio. I believe you have learned something up to this point. So we learned how to perform basic raster operations like opening and getting the values and all that. We learned how to create composites. We also learned how to reproject and clip. This is the beginning of many other tutorials that will show us how to work with raster files in Python. So if you have any questions or concerns, you can leave them down in the comments. I will do my best to respond to all of them. And if you like the video, to make sure to click the thumbs up and consider subscribing if you are new. The code for everything, as always, is in the GitHub repository, which you can find it linked in the description below. Until next time, it is goodbye.